Hi, good morning, everyone. So this last time, I had a presentation about the topics of emission of
It needs to say off like this.
okay, thank you. So last time I had many questions about my mechanism because my idea is based on the solid state physics. Probably this field is unfamiliar with every person. So today I'd like to add some precise explanation and hint on the thinking way, and also add some few examples. What kind of material has this long time so far, the long lifetime of the persistent trail was thought as based on the plasma. The plasma means contains atoms or molecules and ions. So each spectrum comes from these materials. But in case of these spectrum has a very short period, short lifetime, because if these atoms or molecules get energies, then the electron excited a certain level of the energy. After that, the electrons, what should I say, keep the sun light by energy form, then drop down to the ground state. So in this case, the time of this behavior costs very short period, like less than millisecond, or in case picosecond, or like that. But these mechanisms cannot explain the long duration times, like a few seconds, or in case minutes, 10 minutes, 20 minutes, like that. So from this fact, I checked the what should I say, experiments and some mechanism thinking way. So all of them cannot explain long duration time. Then again, I analyze the trail, persistent trail, what kind of behavior, what materials conform of this persistent trail. So these trails keep this tube-like shape, tube-like. And exactly, not only this case, but also nowadays, in the National Observatory of Japan, Dr. Ie observed the trail of the meteorite by using the Subaru telescopes. So very wide field and also the magnified image. Then he also mentioned found the tube-like shape, tube-like trail. So when we think about the tube-like, that means the trail looks like smoke. What is the smoke? Gas? No. The smoke is consists of the very, very small particles, solid particles. Yeah. So solid particles is the hint of the mechanism for explaining this long persistent emission. Okay. Oh, sorry. Next slide, please. So they must compose phase microcluster or dust. So when I say solid small particles, yeah, the size is nanoscale or micron scale or milliscale. So these thinking ways are just the fact of the like a micrometeorite. As you see that the display of the micrometeorite, so size is micrometers or at most 1 millimeter. Okay, so how behave these kind of the small solid particles? Okay, so I checked the optical property of this kind of the material. So please, next slide. Okay, so these particles consist of formed by the ablation of the meteorite when they get into the atmosphere. So condensation, sorry, this phase formed after the gas by the ablation and condensation or crystallization of vapor from the chemical species from the meteorite. Okay. And in case splitting off and separation of non-melt mineral grains from the meteorite itself, so very fast entrance, or yeah, most of them once evaporate into gas, but soon they are from the condensation. Yeah. So this behavior can we see in the on the ground. So engineering standpoint, many fine, much fine particles, nanoscale, can produce by in the vacuum chamber. So once metals or some materials make high temperatures, then they soon form the small particles, nanometer size. This technique has already established in the engineering field. So like that, even some evaporation occurred soon, they will condensate certain size of the solid particle. Yeah, I said solid, but this case, too high temperature. So then the solid itself, okay, in case melted droplets. Okay, so next slide, please. Then the materials, this case, small particles, get heat energy from the ablation. Then this heat energy can translate to the some kind of the form of the energy emission. So heat translate to heat or photon. That means some kind of light emission, including luminescence, or electron or ion in case chemical reaction occur. So these are the emission of the energy or using energy, the excited electron drop down to the ground state. Okay, so next slide, please. Okay, so focus on the heat energy feeding and the grain emit photons by the form for the form of luminescence. This is the one way of the thinking way of light emission from the solid particle. Okay, so these cases. Anyway, please focus on the electron behavior, excited and drop down. But in case of the atoms or molecules, this exciting energy position is just included in atoms or ions, very small space, so-called space. But in case of the solid, you know, solid forms many order of the atoms or molecules. very regularly ordered. Okay, so these species, these atoms or molecules contains electron, but some electrons are used for binding each other. The another electrons used as a kind of the free electron moved. Okay, so this is the difference between the atom or a molecule case and solid case. Okay, so next slide, please. Okay, so by atoms or molecules, electron transition between different orbital potential in the atom or molecule. So probably these figures can you see in the textbooks of the spectrum physics. Okay, but in case of the bisolids, charge unbalanced electron transition between energy potential of regular and deepest crystal lattice. So the point is, these electrons behave in a crystal lattice. And yeah, so please, next slide. When we think about energy level, the horizontal axis means the distance between two atoms. Okay, two atoms. So A0 is just what should I say? The distance of the molecule. Yes, two atoms molecule. Okay, if each atoms are separated far away, the potential energy is this level. You know, in case of silicon, so silicon has the the s orbital, d orbital, and p orbital. Okay, so each orbital has the certain level of energy. That's a straight line. If this both atoms are separated, but approaching to each other, then the potential energy must be a little bit okay. So has the similar energy. That's they generate the energy of in the two atoms. Okay, so in the case of the atom molecules, it contains they generate energy level. But in the case of the solid, each regularly ordered solid atoms has the approach to each other. These levels has some wide band. So in the solid state physics, we call it band structure. Band structure. This is the difference of the solid. Each other on the band. It calls conduct band. So the outside of the each atoms, each electrons has the move freely. In case of the metal, this energy is a little bit closer. Then not only the band energy, but also not only the band energy and this condensed energy. In the condensed band, the electron moves freely. We call it free electron. In the case of the insulator, like many kinds of the rocks and minerals. The valence band and the condense band is separate like that. So this is the key point when we think about rocks or minerals or the meteorite. Okay. So next slide, please. So I must say, energy gap. This energy gap means okay. This energy gap is the difference of valence band energy and conduction band energy. So in insulator case, this energy gap is very wide. Metal is very close. So valence band electron can easily excite or go up to the condensed band. But in insulator case, seldom jump up to the conduction band. Okay. So in the case of the insulator, the electron must get much energy than metals to jump up to the excited state, the energy level of the conduction. Okay, so next slide, please. Okay, probably you know this figure. The electron is allowed to the the one electron can occupy certain level. Okay, so at the temperature of the zero absolute temperature, 0 Kelvin, the distribution is just the what should I say? So straight line down to there. But when this electron get energy by increasing temperature, the distribution is moved like straight solid line and dot line. Okay, so next slide, please. Yes. When we think about the insulators level, okay, the energy band is like that. This figure you may saw the second slide. Okay, so density of state means the possible electron state can occupy. So if they have the gap energy like that, the valence band and conduction band, they had the difference, different gap. And if we think about Fermi-Dirac distribution function, okay, so the electron possibility, existence possibility has this kind of the form. But gradually, if the temperature increase, they had this kind of curve. So this distribution think overlap to this energy band. Okay, so the electron at the zero temperature, 0 Kelvin, the electron is concentrated on a valence band, and increasing temperature, yeah, get energy electron, but not jump up because less of lack of energy to jump up into the valence conduction band. So finally, much high temperature, these electrons can get excited. So in the case of silicon, the band gap is about 9 electron volt. That means the temperature is almost 11,000 Kelvin, like that. Okay, sorry. So next slide, please. This behavior I explained in last year, and this time show some examples about that. So next slide, please. Yeah, so skip. One example is, please skip. That's it. No. Two. Next one. Yes. So the color center defects for the amorphous silicon. So just after the droplet formation in the ablation. So anyway, we can explain these band structures explanation applied to the light emission of the meteorite droplets. Thank you.
Thank you very much. Unfortunately, there is no time for questions.